Okay, thank you. And I really appreciate the invitation to give this talk. It's an honor for me to give a talk in honor of Lou Kaufman. I really thank the organizers for this great congress. And I've known Lou for at least 19 years. I remember when he came to University of South Florida in February 16, 2006. And he gave a lecture. We have this lecture for general audience called Nagel Lecture. And his talk was about unknots, collapsing tangles, and DNA recombination. And since then, I meet him not in Washington, etc. Okay. I will talk a little bit about knot group and Quandles in relation to orderability. This work originated from a question asked by Adam Clay and his co-authors. In one of his papers, he studied the bi-orderability of the knot groups, and he asked the following question. Can non-bi-orderability of knot groups be determined using other invariants other than Alexander polynomial? Now, in their paper, they investigated bi-orderability using Alexander polynomial. Among the results, they showed that the fundamental group of the R-twist knots is bi-orderable if and only R is even. They considered also fundamental group of two bridge knots, and they did some computer calculation also. Okay, my talk will be, I'll start with some review of orderability of groups and quandles. Then I will talk a little bit about the space of ordering. And then the third part will be about bi-orderability of knot groups using quandles. Okay, these definitions are clear, and I assume everyone knows this definition. If you start with a group and you consider an order on it, then the group will be said to be right orderable if the order is preserved by right multiplication. If the order is preserved by left multiplication, we will call it left orderable group. Now, in groups, every left ordering gives right ordering and vice versa. If you have left ordering, you create a new one by this formula. Now, this is for sure not true for quandles, we will see it. Now, we consider the set of right ordering on a group G, and we will denote it by Rho of G. In the same way, we can define left ordering on G as the set of left ordering on the group. And we have one-to-one correspondence between right ordering on the group G and left ordering on the group G. Here, the order small prime is not the same as the order we started with. They don't have to be the same in general. A group on which an order is both left invariant and right invariant is called bi-order. We will give some examples. We have the following example is integers with addition is right orderable. Non-zero real numbers with multiplication cannot be right orderable. Simply because -1 is less than 1, and that will give contradiction if it was right orderable. For abelian groups, bi-orderability is equivalent to torsion-free. We have other ordering on groups like braid group and pure braid group. This is due to Patrick Duhornoy. He defined an ordering on the braid group Bn. Word W of the shape alpha 0 sigma I, alpha 1 is greater than 1. Sigma I is one of the generator. By definition, alpha 0 and alpha 1 are words in the sigma j such j is greater than I, starting from I plus 1 till the last one, sigma n minus 1. For example, one can see that sigma 1 is less than sigma 2 sigma 1. because you can change that to sigma 2, sigma 1, sigma 2 inverse greater than 1. And notice that sigma 2, the index is greater than 1. Notice that sigma 1 inverse sigma 2 sigma 1 is not greater than 1 according to this definition. He also proved that the braid group is not bi-orderable. Now, the pure braid group is orderable. These are some examples of orderability on groups. Sorry. Okay. The group homeoplus of the real line is order preserving maps on the real line is left orderable. The idea of the proof, it goes like this. You take two homeomorphisms F and G which are not equal, and you pick the first xi such that they are distinct, and you define f less than g by definition if f of xi is less than g of xi. And then one can check that it is left, this is left order. Etienne Gis in 2001, he proved that a group G countable is left orderable if and only if it embeds into homeoplus of the real line. Okay, we have the following theorem. If H is a normal subgroup of G, and you take the quotients G over H, if both H and K are left orderable, then the group G is orderable. Now, this gives us the fact that the fundamental group of the Klein bottle, which is generated by XY such that XY X inverse equal Y inverse, is right orderable. But it is not bi-orderable. Then you can have right orderable, which is not bi-orderable, and this is an example. Now, this shows that bi-orderability is not preserved by extension. If you do extension of bi-orderable group by another bi-orderable group, the extension may not be bi-orderable, as this example shows. James Hoey in 1982, he proved this theorem that not groups are left orderable. If G is bi-orderable group and there exists an n such that xy to the n equal y to the nx, then one can prove that xy equal yx. This is basically due to the fact that the n roots are unique. You can solve if you have the xn equal yn, that implies x equal y. As corollary, one obtains that the fundamental group of the torus knot TMN cannot be bi-orderable. The fundamental group of the figure 8 knot is bi-orderable. This is a result of Perron and Rolfson. Tararin in 1991, in his paper titled On Group Having a Finite Number of Right Order, he gave a complete classification of all groups with only finitely many orders. These groups are known as Tararin groups, and his theorem states that if you have a group G, left ordering will be finite if and only if G admits a rational series Tn plus 1, normal subgroup of Tm till the last one T0, which is G, such that there is an element of the quotient Ti by Ti plus 1 whose action by conjugation on Ti plus 1 quotient by Ti plus 2 is by multiplication by negative rational number. If you have a group such that the number of right orders is 2, that's equivalent to T being torsion-free abelian of rank 1. We have the following result. If n is free abelian normal inside G and rank of n is greater than or equal to 2, such that G over n is right orderable, then G has uncountably many different right orders. Now, sometimes we use left order, sometimes we use right order. It's the same because what we saw in the beginning, that left order give right order and vice versa. Peter Linen later used Tararin work to prove the following theorem in 2011. The space of ordering on a group cannot be infinitely countable. In other words, it's either finite or uncountable. Okay, this was a quick review about orderability of groups. Now we're going to review a little bit the basics of Quandle. Then we will talk about orderability of Quandles. Now, a Quandle is set with a binary operation which satisfies the following three conditions. As you know, these conditions come from Reidemeister moves 1, 2, and 3. The first one says that the star operation is idempotent, x star x equal x for every x. The second axiom says that right multiplication by every element, called it R sub x, it's a bijection, and that comes from Reidemeister move 2. It's like R matrix in the Young-Baxter equation. We want it to be bijective. And the third condition, which is basically that right multiplication is an automorphism of the Quandle. In other words, the star distributes on the right on itself. Here are a few examples. I only put few examples because these are the examples we will use in this talk. Any group become a Quandle if you use conjugation on it. If you have a group, you can consider the core group, which is a Quandle, given by the operation x star y is y x inverse y. This is involutory Quandle. Right multiplication are in involutions. And then if you have a module over z of t inverse, Laurent polynomial, it becomes a Quandle with the operation given by x star y equal tx plus 1 minus ty. And this is called Alexander Quandle. Back in 2021, Bardakov, Passy, and Singh in one of their papers defined the notion of right orderability for Quandle and left orderability of Quandle. And the definition is similar to the group case. If S is less than T, right orderability means it's invariant from the right. And left orderability means the order is invariant from the left through the star operation in the Quandle. Among the results, they proved that the conjugation on a group G is the right orderable Quandle, but it is not left orderable. They proved also that the core of the group G is left orderable, but not right orderable. Here is an example. If you consider the real line with its ordering, natural ordering, and you consider basically what is called affine Quandle, similar to Alexander Quandle, x star y equal alpha x plus 1 minus alpha y. We assume that alpha is not 0 and alpha is not y. So we get interest in Quandle. If alpha is greater than 0, then the real line with this binary operation is right orderable Quandle. If alpha is less than 1, then it is left orderable, which give us that when alpha is between 0 and 1, then it is bi-orderable Quandle. Back in 2018, with my colleagues Yun Chang and Boris Schechtman, we used we classified topological Quandles on the real line on the circle. Basically, we were using orderability indirectly. In an article by Rondal, Mahinder Singh and Manpreet Singh, the title is Orderability of Link Quandle in 2021. They proved, first, let's define the enveloping group of the Quandle Q. It's just the free group on Q, and you mode by the relation x star y equal y inverse xy. And clearly, you have a map from Q to enveloping group of Q. And they proved that if this map is injective and the enveloping group is bi-orderable, then the quandle is right orderable. Now, the fundamental group of knot is bi-orderable, implies that the fundamental quandle of the knot is the right orderable. Now, the fundamental quandle of knot is defined in similar way, generated by the arc, and you write a relation at each crossing. And what makes Quandle really good invariant is the theorem by Joyce and Matveev, which says that two knots are equivalent if and only if their fundamental quandle are isomorphic. Then the problem of equivalence of knots is changed to the algebra problem of isomorphism of quandles, which is in general difficult, except if one restricts to some specific families of quandles, then one can achieve higher results or higher classification. They proved also that the fundamental quandle of the torus knot TPQ is not right orderable. For the trefoil, the fundamental quandle of the trefoil is neither right orderable nor left orderable. Now we can define the notion of circular orderability. Now, you remember previously we had orderability is related to homeoplus of the real line. We will see that circular orderability is related to homeoplus of the circle group. Then a circular ordering on a set is just map from 3 copies of T to the set -1, 0, 1, and it satisfies the following two conditions. If any two elements are equal, then it's 0. And if you have 4 elements, T1, T2, T3, T4, you have the following equation. It's basically, this is 2 cocycle. You get rid of T4, and you alternately put plus and minus. Second time, you get rid of T3. You have C of T1, T2, T4, and so on. This is what is called a circular ordering on a set. Now, a group is called right circularly orderable if there is a circular ordering on it, which is invariant from the right. Then C of x, y, z is the same as C of x, g, y, g, z, g. We say that the circular ordering is right invariant. Back in 2021, Idris Abba and Adam Clay, they proved the following theorem, that the set of right circular ordering is finite if and only if the group is either the cyclic group Zn, the finite cyclic group Zn, or G is isomorphic to the semi-direct products of T by Zn, where T is Tararine group. Now, as I mentioned a few minutes ago, if G is countable and left circular orderable, this is equivalent to G can be embedded into homeoplus of the circle S1. We can define right circular orderability on Quandle. Sorry. Okay. The same way we can define a right circular ordering on Quandle, just it's circular ordering on the set, but we require it to be invariant from the right. If it's left circular orderability, we require it to be invariant from the left. Now, back in 2022, we proved that orderability of Quandle implies its circular orderability. Orderability implies circular orderability, but not the other way. Circular or orderable can be finite, while orderable Quandles cannot be finite. And the way to construct a circular ordering when you have an ordering on the Quandle, the idea is just think of S1, S2, S3 on a circle. If you put them on a circle, if they are in this cyclic order, S1 less than S2 less than S3, or S2 less than S3 less than S1, then you make it +1. Otherwise, if you go the opposite direction, it's -1. Otherwise, outside that, you put 0. And one can check that this satisfies the equations of circular orderability. We have the following proposition. If G is a group with circular ordering on it, such that C is both left and right invariant, we can say basically bicircular orderable, then the conjugation Quandle is the right circular orderable. And this is straightforward from the definition. You start with the circular ordering on the group, which is denoted by C, and you define the following map D being the same as C, and one has to check that it's invariant from the right, and the bicircular orderability gives you that. Bicircular orderability of groups have been studied back to 1950s. Precisely in 1959, Sverkovsky, in his paper titled on cyclically ordered group, gave a complete characterization of this type of groups. His theorem states if G is bicircular orderable, then there exists a biorderable group G, such that G is a subgroup of gamma across the circle group. Moreover, the bicircular order on G is determined by the natural bicircular order on gamma cross S1. By the natural bicircular order, it is meant that if you equip gamma cross S1 with the lexicographic bicircular ordering, then the bicircular ordering on G is just the restriction of this lexicographic circular ordering on gamma cross S1 to the subgroup G. One can get a classification of all the subgroups of gamma cross S1, and hence using Sverkovsky theorem, one can obtain infinitely many examples of bicircular orderable group that are not biorderable. Then circular orderability is stronger than orderability, and the same thing, bicircular orderability is stronger than biorderability. Let H be a bicircular orderable group, then its conjugation is right orderable Quandle. And the proof is based on the, you assume that H is biorderable group, then conjugation of H is the right orderable Quandle, and the conjugation of the product H cross S1 is just the product of the conjugation, which is the right orderable as the product of two right orderable Quandles. This is proved in the paper by Rondel, Singh, and Singh. And the result then just follow from Sverkovsky theorem. If G is a group, is non-trivial group with at least 3 elements, then the Quandle conjugation G is not left circular orderable. And the proof is based on the fact that if you pick the identity element and you multiply from the left by the identity element, you can change any for any triple S1, S2, S3. The circular ordering C on S1, S2, S3 becomes just you have C of E, which is 0 because at least this is the same element. If two elements are equal, then the circular ordering is 0. Circular orderability of Quandle is different than orderability, as I mentioned earlier. To be precise, if you take just the simplest Quandle, which is the trivial Quandle with two elements. Now, if you have two elements, every Quandle on it is trivial, meaning right multiplication are identities. This one is bicircular orderable, since the trivial circular ordering, which maps everything to 0, is both left and right invariant. Since this Quandle is not left orderable, this shows that the notion of circular orderability for Quandle is not the same as the notion of orderability. We looked at the small Quandles of cardinality 3 element Quandles, and one can, this is the second Quandle of 3 elements, basically is the set 1, 2, 3, which has the Quandle is given as orbit, it's as the pair 1, 2, and 3. In other words, right multiplication by 1 is identity, right multiplication by 2 is identity, and right multiplication by 3 is the transposition 1, 2. It swaps 1 and 2. This Quandle is neither left nor right circularly orderable. For the left, it is not left invariant because 3 star any element is always 3. And thus you obtain 0. The other way, if you assume that C is right invariant circular ordering on X, then you can prove that C of 1, 2, 3 is C of 2, 1, 3. Now, if you look at 1, 2, 3, imagine 1, 2, 3 are on a circle. 1, 2, 3 goes, say, clockwise. The other one goes counterclockwise. They cannot be equal. When it goes counter, it should be negative. And that comes from the cocycle condition. The last Quandle of 3 element, which is known as the dihedral Quandle, Z3 with operation x star y given by 2x plus y, 2x plus 2y, or minus x plus 2y, since 2 equal minus 1 in Z3. This is neither left nor right circularly orderable. And one can prove it, it's not difficult. Just basically when you have two distinct elements and you star them, you get the third one. That's the property on this Quandle. And then the same thing as in the previous one, you can come up with contradiction, because you can prove that C of xyz is equal to C of zyx. And again, xyz go in one direction, say clockwise. The zyx goes counterclockwise. They cannot be equal because the definition of circular ordering on sets requires that C of xyz should be minus C of zyx. The space of right orders on group G. Back in 2004, Adam Sikora introduced for group G, or even for semi-group, a topology on the right on the set of right orders on G. Precisely, he proved the following theorem, that if G is semi-group, then the set of rights, or the topological space, the set of right orders on G is compact topological space that is totally disconnected. Now, if the group G is just Zn, then this is homeomorphic to the Cantor set. This was generalized to magma by Yosef and his co-authors, Dabkovska and Dabkovsky, Harizanov, back in 2007. And they proved that if X star is magma, basically set with a binary operation, then the set of right orders on X is a compact topological space. Now we prove similar result for a right circular ordering on a Quandle on any Quandle Q. Okay. Now I think I'm at the last part of my talk, and let's talk about knot groups and knot Quandles. Now, a few definitions. I think I mentioned the enveloping quandle earlier. It's just if you have a quandle, you can construct a group from it called the enveloping group of the quandle. Sometimes it's called the adjoint group of the quandle. I think there are a few people use different naming. It's basically generated by the quandle, and you force the condition that the star operation become conjugation. You can consider what is called the n-enveloping group by adding the extra relation that's every element to the power n equal 1. This was defined in the thesis of Joyce. Now, the involutory quandle Q2 of L cannot be right circularly orderable. On the other hand, there are infinitely many links for which their two enveloping group is right circularly orderable. Now, we proved the following theorem. There are infinitely many links for which the enveloping group 2 is right circular orderable. Precisely, if you start with the torus link TPQ, assume that P is greater than 3 and Q is greater than 5. Gordon and Liedman proved that the pi1 of the double branch cover of L is right orderable. This is theorem in their paper titled Tot Foliation, Left Orderability and Cyclic Branch Cover. Now, since pi1 of the double branch cover is an index 2 subgroup of the enveloping group of the fundamental quandle of L, we have the short exact sequence. Now, Z2 is cyclic orderable. The fundamental group of the double branch cover is circular orderable. Then you obtain the enveloping group two of the fundamental quandle of the link is right circular orderable by lexicographic circular ordering. It was shown by Yin Hu in the paper titled Left Orderability and Cyclic Branch Covering, theorem 4.3 on page 401, that for any PQ to bridge a knot with P congruent to 3 mod 4, there are only finitely many cyclic branch cover whose fundamental group are not right orderable. I think this paper is published in the Journal of Algebraic and Geometric Topology. Thus, we have the following proposition giving infinitely many links for which the n enveloping group of their fundamental quandle is right circularly orderable. Now, as in the previous theorem, you just consider now L to be the PQ2 bridge knot with the condition that P is congruent to 3 mod 4 for n sufficiently large prime number. The group enveloping n of the fundamental quandle of L is right orderable. One may ask why the condition n being prime? Because Zn is circularly orderable only when n is prime. For example, Z2 cross Z3 is not circular orderable. In other words, Z6 is not circularly orderable. It is not known exactly which links in the 3 sphere have bi-orderable link groups. In the paper of Joyce, he proved the following theorem. if L is an oriented link in the three-sphere, the enveloping group of the fundamental quandle is isomorphic to the link group, the link group of L. Ryder proved the following theorem. If L is an oriented link in the three-sphere, the quandle homomorphism, the natural quandle homomorphism from the fundamental quandle of the link L to the conjugation quandle of the group enveloping of the fundamental quandle of Q, mapping Q to Q by Q tilde, is injective if and only if L is prime. Combining these two theorems and the fact that conjugation quandle of bi-orderable group is right orderable quandle, we have the following corollary. If L is an oriented prime link in the three spheres such that the link quandle Q of L is not right orderable, then the fundamental group of L is not bicircular orderable. In particular, the link group is not bi-orderable. And this gives a positive answer to a question I mentioned in the beginning by Adam Clay and his co-authors in their paper titled Testing Bi-Orderability of Knot Groups. And the question precisely stated as, can non-bi-orderability of a knot group be determined by examining knot invariant other than the Alexander polynomial? Now, in their paper, they used Alexander polynomial to study bi-orderability of knot groups. Now, here is a nice presentation of the fundamental quandle of the torus knot TMN. This is taken from the paper of Randall, Mahendra Singh, and Manpreet Singh. It's given by M generator A1 AM such that AI is A sub n plus I star AN till A1 with the following conditions: that A sub mj plus k is the same as AK for every integer z, and k is between 1 and m. Now, assume that we have the following theorem. Assume that m and n is greater than or equal to 2, such that no one is multiple of the other. If the torus knot TMN is non-trivial torus link, then its link quandle is not right orderable. Hence, we have the following result. The knot group of non-trivial torus knot is not bicircular orderable. That's it. Thank you. And Lou, happy birthday.
Thank you very much.
I think I finished a few minutes earlier.